Introduction to AWS STS Assume Role. Welcome to our comprehensive deep dive into AWS Security Token Service and the Assume Role functionality. This is one of the most critical security features in AWS that every cloud engineer must master. Throughout this presentation, we'll explore not just the how, but the why behind Assume Role operations. We'll cover everything from basic concepts to advanced cross-account scenarios, complete with real-world implementation examples. Think of Assume Role as AWS's way of implementing temporary security clearances. Just like in a government facility, where you might get a temporary badge to access specific areas, AWS Assume Role gives you temporary credentials to access specific resources. This presentation will take you through 20-plus slides covering architecture, implementation, troubleshooting, and best practices. By the end, you'll be confident implementing Assume Role in any AWS environment. Understanding AWS STS, let's start with the foundation. AWS Security Token Service, or STS. This is the core service that makes the Assume Role function possible, and understanding it is crucial to everything we'll discuss. STS is essentially AWS's credential vending machine. When you need temporary access to resources, STS is what issues those short-lived credentials. Think of it as a secure token dispenser that validates your identity and grants you exactly the access you need for the specific duration you need it. The key advantage of STS is that it's a global service, meaning you can use it from anywhere in the world. However, the tokens it issues can be region-specific when necessary. This provides both flexibility and security. What makes STS particularly powerful is its integration with IAM. While IAM manages long-term identities and permissions, STS handles the temporary delegation of those permissions. This separation of concerns is what makes AWS security so robust. Now let's dive into the core concepts that make Assume Role work. There are several key players in this process, and understanding their roles is essential. First, we have the principal. This is who wants to assume the role. It could be a user, another role, or even an AWS service like EC2 or Lambda. The principal is essentially the requester. Then we have the target role. This is what the principal wants to become temporarily. The target role has specific permissions attached to it that define what actions can be performed. The trust relationship is the policy that defines which principals are allowed to assume the target role. This is your first line of defense. If the trust relationship doesn't allow it, the assumption fails immediately. Finally, we have the session, the temporary identity created when assumption succeeds. This session has its own unique ARN and limited lifetime. High-level architecture overview. Let me walk you through the high-level architecture of how the Assume Role process works. This diagram shows the complete flow, from the initial request to the final resource access. The process starts when a principal makes an Assume Role API call to STS. This call includes the ARN of the role they want to assume, along with any required parameters, like an external ID or session duration. STS then performs several validation steps. First, it checks the role's trust policy to see if the requesting principal is allowed to assume that role. If that passes, it validates any conditions, like IP restrictions or MFA requirements. Once validation succeeds, STS generates temporary credentials, consisting of an access key, secret key, and session token. These credentials are then associated with the target role's permissions. The principal can then use these temporary credentials to access AWS resources according to the role's permission policies. This entire process typically takes just a few seconds. Trust Policy Deep Dive. The trust policy is absolutely critical to understand because it's the gatekeeper for Assume Role operations. Let me break down exactly how trust policies work and why they're structured the way they are. A trust policy is a specific type of IAM policy that's attached to a role. Unlike permission policies that define what actions a role can perform, trust policies define who can assume the role in the first place. The principal element in a trust policy can reference AWS accounts, specific users, roles, or even AWS services. You can be very granular here. You might allow only specific users from specific accounts to assume a role. Conditions in trust policies add an extra layer of security. Common conditions include requiring an external ID to prevent the confused deputy problem, IP address restrictions, or MFA requirements. Remember, trust policies are evaluated before any permission policies. If the trust policy denies the assumption, the process stops there. The principal never gets temporary credentials. Let's examine the actual JSON structure of a trust policy. Understanding this syntax is crucial because you'll be writing these policies frequently in real-world scenarios. The version field should always be the 17th of October 2012. This is the current version of the IAM policy language. The statement array contains one or more policy statements that define the trust relationship. Each statement has an effect that's either allow or deny. For trust policies, you'll typically use allow to grant assumption rights. The action should be STS Assume Role for Assume Role operations. The principal is where you specify who can assume the role. You can use account IDs, user ARNs, role ARNs, or service principals like ec2.amazonos.com for EC2 instances. Conditions are optional but highly recommended for security. The external ID condition prevents the confused deputy attack, while IP conditions restrict access to specific networks. Let's talk about permission policies versus trust policies. This is a concept that confuses many people, so let me clearly explain the difference between permission policies and trust policies, and how they work together. Think of trust policies as the front door security guard. They check if you're on the guest list and allowed to enter the building. Permission policies are like the access cards that determine which rooms you can enter once you're inside. Trust policies answer the question, WHO can assume this role. They're attached to the role itself and evaluated by STS when someone tries to assume the role. Permission policies answer the question, what can this role do? They define the actual AWS permissions that the role grants, like reading S.3 objects or creating EC2 instances. Both types of policies must allow an action for it to succeed. If the trust policy allows assumption but the permission policy doesn't grant the necessary permissions, you'll be able to assume the role but unable to perform the desired actions. The AssumeRole API call. Now let's look at the actual API call that makes everything happen, the AssumeRole operation. This is where the rubber meets the road in terms of implementation. The AssumeRole API is part of AWS STS, and it's what your applications, scripts, or users call when they need to assume a role. The API is simple but powerful with several important parameters. The role ARN parameter specifies exactly which role you want to assume. This must be the complete ARN, including account ID and role name. The role session name is a required identifier for the session. Make it meaningful for auditing purposes. The external ID parameter is crucial for security in cross-account scenarios. It must match what's specified in the role's trust policy. Duration specifies how long the credentials should be valid, from 15 minutes to 12 hours. You can also pass additional policies to further restrict the session's permissions beyond what the role normally allows. This is useful for implementing least privilege access. STS response and temporary credentials. When the AssumeRole call succeeds, STS returns a response containing temporary credentials and metadata about the assumed role session. Let's look at what you get back and how to use it. The credentials object contains 3 key pieces: access key ID, secret access key, and session token. All 3 are required to authenticate API calls. You can't use just the access key and secret key as with long-term credentials. The expiration timestamp tells you exactly when these credentials will stop working. It's crucial to track this and refresh credentials before they expire, especially in long-running applications. The AssumeRole user object provides metadata about the session, including a unique AssumeRole ID and the session ARN. This information is useful for logging and auditing purposes. These temporary credentials work with all AWS SDKs and CLI tools, but remember, they have a limited lifetime and must be refreshed periodically. Setting up your first AssumeRole. Let's walk through the step-by-step process of setting up your first AssumeRole scenario. I'll show you the exact commands and explain what each one does. First, we need to create the IAM role that will be assumed. This involves defining the trust policy that specifies who can assume the role. The trust policy is provided during role creation using the Assume Role policy document parameter. In our example, we're creating a role that can be assumed by entities in a specific AWS account. The external ID adds an extra layer of security. Think of it as a password that the assuming party must know. The role creation returns important information, including the role ARN, which you'll need for assumption operations. The role ID is also generated. This is a unique identifier that AWS uses internally. Once the role exists, you can modify its trust policy later using the update AssumeRole policy command if needed. However, it's best to get the trust policy right from the start. Attaching permission policies. Creating the role is just the first step. Now we need to give it actual permissions by attaching policies. This is where you define what the role can actually do once assumed. You can attach AWS managed policies, which are pre-built policies maintained by AWS, or custom policies that you create. AWS managed policies are great for common use cases like read-only access or power user access. For more specific requirements, you'll create custom policies. These should follow the principle of least privilege, grant only the minimum permissions necessary for the intended use case. The policy we're attaching here allows specific S.3 operations on specific buckets. Notice how we use both bucket level and object level permissions, and we include a condition that requires objects to have a specific tag. You can attach multiple policies to a single role, and the effective permissions are the union of all attached policies, subject to any explicit deny statements. Configuring the source identity. Now let's set up the source identity. This is the user, role, or service that will assume our target role. This is an often overlooked but crucial step in the AssumeRole setup. The source identity needs explicit permission to assume roles. Just because a role's trust policy allows a principal to assume it, doesn't mean that principal automatically has the STS Assume Role permission. This creates a two-way security check. The source must have permission to assume roles, and the target role must trust the source. Both conditions must be met for assumption to succeed. In our example, we're creating a dedicated user for Assume Role operations and granting it permission to assume only the specific role we created. This follows the principle of least privilege. The resource ARN in the policy should match exactly the role ARN from our previous step. Any mismatch will result in access denied errors when you try to assume the role. Now we'll look at executing the Assume Role operation. This is where all our previous configuration work pays off, leading to the retrieval of our temporary credentials. The AWS CLI command shown here includes all the key parameters we discussed earlier. The role ARN specifies which role to assume, and the session name helps with auditing and tracking. The external ID must match exactly what we specified in the trust policy. This is case sensitive, and any mismatch will result in an access denied error. The duration is set to 3,600 seconds or 1 hour in this example. You can adjust this based on your needs, but remember that shorter durations are more secure as they limit the window of exposure if credentials are compromised. When this command succeeds, you'll get back the temporary credentials that you can use to access AWS resources with the permissions of the assumed role. Once you have temporary credentials, you need to know how to use them effectively. There are several methods, each with its own use cases and advantages. Environment variables are the most straightforward method for scripts and applications. You set the environment variables AWS_access_key_ID, AWS_secret_access_key, and AWS_session_token, and the AWS SDK or CLI automatically uses them. AWS CLI profiles are great for interactive use or when you need to switch between different sets of credentials. You can create a named profile with the temporary credentials and specify it in CLI commands. For applications, you typically want to handle credential refresh automatically. Most AWS SDKs provide credential providers that can automatically refresh AssumeRole credentials when they're about to expire. Remember that temporary credentials include a session token in addition to the access key and secret key. All three components must be provided for authentication to work. Cross-account Assume Role architecture. One of the most powerful use cases for Assume Role is cross-account access. This allows you to securely access resources in different AWS accounts without sharing long-term credentials. The architecture shown here is a common pattern in enterprise environments. You have a development account where your teams work and a production account that contains critical resources. Instead of giving developers direct access to production, you create roles in the production account that can be assumed by specific identities in the development account. This provides auditability and the ability to grant time-limited access. The trust relationship flows from the production account's role back to the development account. The role in production trusts specific entities in development to assume it. This pattern scales well. You can have multiple accounts for different environments, such as development, test, staging, and production, and use AssumeRole to control access between them. Cross-account setup commands. Let's look at the specific commands needed to set up cross-account AssumeRole. This is where many people make mistakes, so I'll walk through each step carefully. In the target account production in our example, you create a role with a trust policy that specifies the source account or specific entities in that account. The principal ARN must be exact. Any typos will prevent assumption. The external ID is particularly important in cross-account scenarios because it helps prevent the confused deputy problem. This is where a third party might trick you into performing actions on their behalf. In the source account development, you need to grant permission to assume the role in the target account. This permission is typically attached to users, groups, or roles that need cross-account access. Notice how the resource ARN in the source account policy must exactly match the role ARN in the target account. Account IDs must be correct, and the role name must match exactly. When implementing AssumeRole, particularly in production environments, security is paramount. Here are the key best practices to ensure your implementations remain secure. Always use external IDs for cross-account access. This simple addition prevents confused deputy attacks, where a malicious third party tricks you into performing actions on their behalf. Make your external IDs long, random, and unique. Implement the principle of least privilege ruthlessly. Don't attach broad policies like power user access unless absolutely necessary. Create custom policies that grant only the specific permissions needed. Use IP address restrictions in trust policies when possible. If your applications run from known IP ranges, add those as conditions in the trust policy to prevent access from unauthorized locations. Require MFA for sensitive operations. You can add MFA conditions to trust policies, requiring users to authenticate with a second factor before they can assume roles. Monitor AssumeRole operations using CloudTrail. Every assumption generates events that you should analyze for suspicious activity. Common troubleshooting issues. Even experienced engineers encounter issues when implementing AssumeRoles. Let me walk you through the most common problems and how to diagnose them quickly. The troubleshooting flowchart shows the decision tree that STS follows when processing AssumeRole requests. Most failures happen at 3 points: trust policy validation, source permission checking, and condition evaluation. Trust policy issues are the most common. Check that the principal in the trust policy exactly matches the ARN of the entity trying to assume the role. Account IDs, usernames, and role names must be exact. Source permission issues occur when the assuming entity doesn't have STS AssumeRole permission. This is particularly common when setting up cross-account access for the first time. Condition failures often involve external IDs, IP restrictions, or MFA requirements. Make sure external IDs match exactly between the trust policy and the AssumeRole call. Check that IP addresses are correctly specified and that MFA is provided when required. Error messages and solutions. Let's look at specific error messages you might encounter and how to resolve them. Understanding these errors will save you hours of debugging time. The error "not authorized to perform STS AssumeRole" is very common. It means the source identity lacks permission to assume roles. Add an explicit policy granting STS AssumeRole permission for the specific role. ARN signature mismatch errors usually indicate clock skew problems or incorrect credentials. Ensure your system time is synchronized with NTP and verify that you're using the correct access keys. Access denied errors when using temporary credentials suggest that the assumed role lacks the necessary permissions for the actions you're trying to perform. Check the role's attached policies and ensure they grant the required permissions. The debugging commands shown here are invaluable for troubleshooting. Use getCallerIdentity to verify who you're authenticated as, and use the IAM policy simulator to test permissions before deploying to production. Advanced use cases. Now let's explore some advanced use cases that demonstrate the real power of AssumeRole in enterprise environments. These patterns solve complex real-world problems. Role chaining allows you to assume multiple roles in sequence. For example, you might assume a role in a shared services account, then use that role to assume another role in a production account. This enables complex access patterns while maintaining security. Service-linked roles are special roles that AWS services assume on your behalf. When you enable certain AWS services, they automatically create and assume roles to perform actions in your account. Federation scenarios involve external identity providers like Active Directory. Users authenticate with their corporate credentials, and temporary AWS credentials are issued through AssumeRole operations. Programmatic credential refresh is crucial for long-running applications. Implement logic to refresh credentials before they expire, handling any errors gracefully. Monitoring and auditing. Proper monitoring and auditing of AssumeRole operations is crucial for security and compliance. Let me show you what to monitor and how to set up effective alerting. CloudTrail captures every AssumeRole operation, including who assumed what role, when, and from which IP address. Set up CloudTrail in all accounts and ensure logs are sent to a central S3 bucket. Key events to monitor include AssumeRole API calls, particularly failed attempts or assumptions from unexpected IP addresses. Also monitor for unusual patterns like the same role being assumed multiple times in quick succession. Set up CloudWatch alarms for suspicious activity. For example, alert on failed AssumeRole attempts from unknown IP addresses or successful assumptions outside of business hours. Use AWS config to monitor changes to role trust policies and attached permissions. Any modifications to these policies should be reviewed and approved through your change management process. Consider using AWS Access Analyzer to identify external access to your roles and ensure that cross-account access is intentional and properly configured. Performance and optimization. Let's discuss performance considerations and optimization techniques for AssumeRole operations, which are especially important in high-throughput applications. AssumeRole calls typically take 200 to 500 milliseconds, which can add up in applications that make frequent API calls. Cache temporary credentials and reuse them until they are close to expiration. Implement credential refresh logic that refreshes credentials when they have 5 to 10 minutes remaining. This prevents last-minute refresh failures and ensures smooth operation. For applications that assume multiple roles, consider using connection pooling and credential caching to minimize the number of AssumeRole calls. Each role's credentials can be cached independently. Be aware of AssumeRole API limits. STS has regional limits on the number of AssumeRole calls per second. If you hit these limits, implement exponential backoff with jitter in your retry logic. Consider using IAM roles for EC2 instances instead of AssumeRole when possible, as instance metadata credentials are automatically refreshed without API calls. Integration with DevOps workflows. Role assumption integrates beautifully with modern DevOps practices. Let me show you how to incorporate role assumption into your CI/CD pipelines and deployment workflows. In CI/CD environments, use role assumption to grant deployment pipelines access to target environments without storing long-term credentials. Each pipeline job can assume the appropriate role for its deployment target. Create different roles for different stages of your pipeline. For example, a testing role might have read-only access to validate deployments, while a deployment role has write access to update resources. Use GitHub Actions or similar tools with OIDC providers to enable keyless authentication. Your CI/CD system can assume roles without storing any AWS credentials. Implement approval workflows where sensitive roles require manual approval before assumption. This adds a human checkpoint for critical operations. Tag your resources with environment and ownership information. Then use these tags in role policies to automatically restrict access to appropriate resources. Conclusion and next steps. Congratulations, you've now completed a comprehensive deep dive into AWS STS Assume Role. Let me summarize the key takeaways and suggest next steps for your learning journey. Remember that Assume Role is fundamentally about temporary delegation of permissions. The trust policy controls who can assume a role, while permission policies control what the role can do. Security should always be your top priority. Use external IDs, IP restrictions, and MFA when appropriate. Monitor all Assume Role operations and implement automated alerting for suspicious activity. Start simple with same account role assumptions, then progress to cross-account scenarios as you become more comfortable. Practice with non-production accounts first. Your next steps should include implementing Assume Role in a test environment, setting up CloudTrail monitoring, and creating standardized role templates for your organization. Keep learning. AWS security is constantly evolving, and Assume Role is just one part of a comprehensive security strategy. Thank you for your attention, and good luck with your implementations.